All right, part 3 in this series on EXC. And we're going to take a look now at the generalized gradient approximation. So once again, this is a repeat from the last video. Here are the Kohn-Sham equations for the individual orbitals. And what we're looking for is VXC here. Anything else we know how to calculate. Now we want to improve on the local density approximation because, it could have been fine, but it's crude for bond strengths. And probably crude is charitable. It's okay for lengths and frequencies, but chemists want more than that. It's just not accurate enough to do chemistry. So what could we do to improve things? Well, I keep coming back to this figure because there's a lot in it, and I'm not sure they made all they could have on it. Let's take a look at this contour right here. Let me see if I can change. There we go. This contour right here. So, there's the one right around the ridge and the second one. So I go around here and they all have the same density. So they would all have the same contribution to EXC based on the fact that the only thing that matters in the local density approximation is the density. On the other hand, take a look at the gradient of that density. Here's like a topographic map, right? When it spreads out like this, it's changing slowly. When the lines are close to one another, it's changing rapidly. It's a little hard to believe that this density and this density are equivalent in terms of EXC, just because the density is changing in different ways for those two. And that's all the gradient expansion approximation, or the GGA, is about. Building in the information that says this density is not equivalent to this because they have different rates of change with position. So here's what they did. It's called the gradient expansion approximation. And look, this is a Taylor series. It's the complicated Taylor series. Let's not be clever. It says that EXC depends like the local density approximation, but then builds in terms that have to do with the density changing with position. And that was a clever idea. And you can imagine that expansion going out now. But the problem is, by just doing this, so all you've done is build in information about the gradient at one point. Now you know that that can't be right everywhere, right? It's just not a straight line for the density. You're treating it as if it were. And when you integrate over all space, it breaks properties of the exchange hole. It makes things worse. So the exchange hole now can be positive, needn't integrate to 1. The things that LDA got right, you think you fixed part of it, but then you broke part of it. Now, it might have been that that's not a big deal, but it turns out it is a big deal. The gradient expansion turns out to be totally useless and a disaster. So if that's all we had, we'd be sticking with LDA. But the Purdue group, and actually probably the Langer group before them, had this very clever idea. They said, look, I'm going to look at all the pieces in a gradient expansion, and what I'm going to do is I'm going to truncate it, and I'm going to throw out all the terms that break the exchange hole and the correlation hole. So what they're going to look at is they're basically going to do an integral until it's the case right up to the point where hx integrates to -1 and is always negative, and the correlation hole integrates to 0. And after that, they throw out all the terms. What do you get? Well, you get the impacts of gradients, you get good holes again, and you get better physics. And so these are written in this form, that there's a function of density for both alpha and beta spin and gradients alpha and beta spin that gives you the exchange correlation. It's a little complicated, but that's what it is. And still going to break it up in terms of exchange and correlation. Now, the question is, how much does the density change and where is it important? So they write it as what's called a reduced gradient, and that is the gradient of rho divided by rho to the 4/3. That's dimensionless. And then the question is, where are the important regions here? Well, you can imagine some important regions have to be where the density is big, and if the gradient's not too big, that means S is small. You could imagine that there are regions where the density's kind of changing a fair bit, and maybe the density's not too big, so that might be important for atoms as they decay, or molecules away from the nucleus. And you might imagine there are regions where the gradient is big and the density is really tiny, and there are. But energetically, they tend not to be important. There's not a lot of energy in the tails. So the place we got to get it right is right there, right there. S from 0 to 3. And here is a look at, or a comparison of several exchange GGAs, generalized gradient approximations. So here's the Becca 88, that's part of B3LIP. Here's the PBE, here's Purdue 91, here's LDA, just flat like that. And in this case, they chose to call X sigma what we call S. So this is S, the reduced gradient. And this is basically a term that multiplies LDA. So it modifies LDA for each of these functions. And what you see is, while LDA is flat, all of them are bigger than LDA at small s. Go up, and then they start to be different. So Becca 88 just goes on a straight line like that. We know why it is. PBE flattens out. Purdue Wang 91 is sort of like that, but then it dies off like this. And then revised PBE does this. That looks horrible, right? They're all so different out here. But it turns out this whole area doesn't matter much because there's not much electron density out there. All that matters is in here, and they all behave pretty darn similarly in that region. So all of these exchange functionals work pretty, the GGAs work pretty well because they get the right physics in this region, and they get radically different physics in this region. The GGA generally at small s tends to increase the exchange correlation, EX. They're all pretty similar at short s. They vary wildly at large s, but that's little impact, except if you're worried about van der Waals contacts, and we will come back to that. There is energy density that you care about, and those radically different values give you kind of nonsense. Correlation GGA behaves similarly, but they're much less transparent to me, so I'm not going to make a big deal. If you want to talk about it, we can. And we talk about this as semi-local information. You know, there's some terminology in here that drives me nuts. So these are all evaluated at a point. That's the local part. But in comparison to LDA, it's not just the density at the point, it's the change in density at that point. So it's not really just purely local, so they call it semi-local. Hybrid functionals would be purely non-local. But the point is, we're building information about the shape of rho, which modifies the energy contribution of given density. And coming back here, we're being very clever about the terms related to the shape of rho and which ones we keep and which ones we don't. That's what makes it the generalized gradient approximation. Makes it more complicated to compute, but gives better results, as you've almost seen. Okay, so one last bit, and then we'll talk about, well, if I'm going to shut this thing down. There we go. Then we'll talk about hybrids.